Your phone is constantly measuring the force of the entire planet pulling on it. Even when it's sitting perfectly still on a table, a sensor smaller than a millimeter is detecting gravity itself, 9.81 meters per second squared, every single moment since smartphones started, including accelerometers in 2008. Today we're breaking down every sensor hidden inside your smartphone and exactly how they work, starting with the one that never stops working. Accelerometer. The accelerometer in your phone isn't just detecting motion, it's measuring gravity. Right now, as your phone sits motionless, that tiny chip is reading exactly 9.81 ms2, the acceleration of Earth's gravity pulling down on a microscopic mass inside the sensor. That measurement has been continuous since the iPhone 3G launched in July 2008. Here's how it works. MEMS accelerometers use a spring and capacitor design. A tiny mass hangs on a spring between capacitor plates. When the phone moves, the mass shifts. That displacement changes the capacitance. The sensor translates that electrical change into acceleration data. The entire mechanism is smaller than a millimeter. Your phone measures acceleration in 3 dimensions using multiple accelerometers positioned along X, Y, and Z axes. Modern smartphones pair this with a gyroscope for 6-axis motion tracking. The accelerometer handles linear acceleration. The gyroscope handles angular velocity. That gravity measurement, it's the feature. When the accelerometer detects 9.81 ms2 on the z-axis and near 0 on x and y, the phone knows it's lying flat. Tilt it, and the gravity vector shifts across the axis. That's how screen rotation works. The applications go way beyond flipping your screen. Fall detection for medical alerts, step counting, earthquake monitoring, even airbag deployment in cars uses the exact same technology. The accelerometer measures sudden deceleration, triggers the airbag, saves your life. But if you think measuring gravity is impressive, the next sensor measures something even more fundamental: rotation itself without any moving part. Gyroscope. Your phone doesn't actually have a spinning gyroscope inside it. I know that sounds insane, but hear me out. Every smartphone gyroscope is a MEMS device, which stands for Microelectromechanical System. Instead of a spinning wheel like you'd find in an aircraft, it uses 2 tiny tuning fork arms that vibrate in opposite directions at extremely high frequency. When you rotate your phone, these vibrating arms experience something called the Coriolis effect. The Coriolis effect is the same force that makes hurricanes spin, and in this context, it causes the vibrating arms to bend slightly during rotation. That microscopic bending creates a detectable electrical signal that tells the phone exactly how fast it's spinning in 3-dimensional space. Apple's iPhone 4 in 2010 made gyroscopes standard in smartphones specifically for motion-based gaming, and that single decision changed mobile gaming forever. Before the iPhone 4, tilt controls felt clunky because accelerometers alone couldn't distinguish between tilting and actual rotation. The gyroscope fixed that by measuring angular velocity directly, meaning it knows the difference between you moving the phone sideways versus rotating it in place. Modern gyroscopes handle multiple functions simultaneously. Image stabilization in your camera corrects for hand trembling in real time by detecting micro rotations and compensating instantly. Auto rotation switches your screen from portrait to landscape by sensing when you physically rotated the device 90 degrees. And 3D motion tracking in VR headsets and racing games creates immersive experiences because the gyroscope detects even the smallest head or hand movements with precision. But at least the gyroscope uses predictable physics, unlike the next sensor, which literally measures invisible magnetic fields that constantly shift depending on where you're standing. Magnetometer. Here's the thing about smartphone motion sensors. Accelerometers and gyroscopes are constantly calculating your position by tracking, but there's a problem. Every single calculation introduces tiny errors that compound over time. Leave a gyroscope running for an hour and it'll drift significantly, sometimes by dozens of degrees when you haven't moved at all. This phenomenon is called drift, and it's the reason navigation systems constantly need recalibration, but one sensor drifts far less than the others, and it's the only one measuring something external, your higher. The magnetometer. Most modern smartphones contain a magnetometer that detects Earth's magnetic field, and it's the only motion sensor that measures something real instead of calculating accumulated change, right? While accelerometers and gyroscopes burn through substantial power, magnetometers sip roughly 1/10 to 1/100th the energy. It's measuring an external reference that exists independently of your device, the planet's magnetic field. And because it's not computing anything through integration, it doesn't accumulate errors the same way. Your compass app maintains its accuracy dramatically better than gyroscopes or accelerometers over time. Minimal drift compared to everything else. So if magnetometers are so accurate, why do you have to calibrate them? Great question. The sensor itself is solid. The problem is everything around it. Your phone is full of metal components, electrical currents, and magnets that create local magnetic interference. The battery generates field. The speaker contains magnets. So when you wave your phone in a figure-8 pattern during calibration, you're not fixing the sensor. You're teaching it to compensate for all the magnetic garbage inside your phone. The calibration exposes the magnetometer to every possible orientation so it can map out which distortions come from your device versus which come from Earth. Once calibrated, it knows the difference. At least it's more reliable than gyroscopes, unlike the sensor that's been secretly watching your face this entire time. Proximity sensor, your phone is watching your face right now, and you have no idea it's happening. Here's the thing. Every time you make a phone call, an invisible infrared beam fires out from near your front camera and scans your face continuously. It's measuring exactly how far away you are from the screen, and the moment you cross within 10 centimeters, it kills the display and disables the entire touchscreen. The sensor itself is absurdly simple. An infrared LED emitter shoots out invisible light, and a photodiode receiver sits right next to it, waiting to catch the reflection. When light bounces back brighter, you're closer. When it bounces back dimmer, you're farther. The sensor translates these brightness variations into precise distance calculations between 10 and 100 millimeters without any visible indication that measurement is even occurring. During calls, this happens constantly. The infrared beam never stops scanning. The sensor never stops measuring, and your phone never stops deciding whether your face is close enough to warrant shutting everything down. This prevents pocket dials, accidental screen taps during conversations, and battery drain from pointless display activity while the phone is pressed against your head. But it's not just calls. Proximity sensors enable gesture controls across the entire operating system. Wave to wake lets you activate the screen by moving your hand near the sensor. Wave to mute silences notifications with a quick hand gesture. Some phones even let you scroll through content or flip between apps using nothing but hand proximity. All of this happens through reflected infrared light intensity measurement. No cameras, no complex image processing, just a tiny LED photodiode pair continuously firing invisible beams and calculating distances based on how much light comes back. At least it's only monitoring your face during active use, unlike the sensor that's been quietly photographing your screen interactions without permission. Ambient light sensor. Your phone's auto brightness feature seems harmless. It dims your screen in the dark, brightens it in sunlight. That's it. Right? Wrong. In January 2024, MIT researchers published findings that should genuinely concern you. The ambient light sensor responsible for adjusting your screen brightness can be weaponized into an imaging device, and I'm not talking theoretical future tech. I mean right now, with the sensor already in your phone. Here's how it works. The sensor uses your display as a lens. When you swipe, tap, scroll, pinch, or rotate on the screen, computational imaging algorithms can capture those interactions. The sensor detects the changes in reflected light created by your hand movements and reconstructs images of what you're doing. One frame every 3.3 minutes. Not fast, but fast enough to capture passwords, pins, browsing patterns. The truly disturbing part, apps can access ambient light sensor data without requesting permission. Unlike your camera, which triggers an explicit authorization prompt and shows an indicator light when active, the ambient light sensor operates silently. No notification, no indicator, no way to know it's recording your gestures. Originally, this sensor was designed with one simple job: measure light intensity and adjust screen brightness accordingly. That's it. A purely environmental sensor. But because it technically measures reflected light from the display, It can detect the shadows and brightness variations created by your fingers moving across the screen. Right now, the thread is limited. One frame every 3.3 minutes means practical exploitation is difficult. You'd need the victim to perform the same interaction repeatedly during the capture window. But sensors are getting faster. The next generation could theoretically capture interactions in real time. At least you can turn off auto brightness if you're paranoid. Unlike the next sensor, which operates whether you want it to or not, the barometer, your phone knows exactly how high above sea level you are right now, and it's measuring that by weighing the entire atmosphere. Before you assume that's impossible, hear me out. There's a sensor in your phone smaller than a grain of rice called a barometer, and it's measuring atmospheric pressure with 24-bit resolution. That means it can detect incredibly tiny changes in air pressure, and air pressure changes predictably with altitude. Here's how it works. At sea level, the weight of all the air above you creates exactly 1,325 pascals of pressure. But as you climb higher, there's less atmosphere above you, so the pressure drops. For every 100 meters you gain in elevation, atmospheric pressure decreases by approximately 1.2 kilopascals. Your phone's barometer measures that pressure change constantly. Drop your phone on a table and it registers one pressure reading. Carry it up a flight of stairs and it detects the pressure decrease. The sensor knows you've climbed based purely on how much lighter the air got. The sensor itself is a micro-electromechanical system built on microscopic scale. It contains a tiny sealed chamber with a flexible membrane. When external air pressure changes, that membrane flexes and capacitive sensors measure the deflection with extraordinary precision. The Bosch BMP390, one of the most common smartphone barometers, can resolve altitude changes as small as 10. This is the exact same principle aircraft altimeters use. Your phone does the identical calculation, just in a package millions of times smaller. But here's where it gets useful. Weather apps use barometric data to predict incoming storms when pressure drops rapidly. Fitness trackers calculate elevation gain during hikes, giving you credit for every meter climbed. Some emergency systems monitor sudden pressure changes to detect falls, and unlike GPS, which can fail indoors or in dense urban areas, barometric altitude works everywhere. GPS tells you latitude and longitude, but the barometer tells you the third dimension continuously in real time without needing any external signal. But at least your phone isn't scanning your fingerprint in 3 dimensions using ultrasonic sound waves. Oh wait, biometric sensors. Your phone unlocks when you touch it. Simple, right? But here's the thing. 3 completely different technologies are fighting for dominance in your fingerprint sensor, and they work in ways most people would never guess. The most common type is capacitive. When your finger touches the sensor, it creates a tiny electrical field. The ridges of your fingerprint conduct electricity better than the air-filled valleys. So the sensor measures voltage changes across thousands of microscopic electrodes. It's mapping your finger electrically, pixel by pixel. Optical sensors are simpler but less secure. They just take a photograph of your finger using light reflection. Bright light hits your finger, bounces back, and a camera captures the pattern, which is why they can be fooled by high-resolution photos or fake fingerprints. Not ideal. But ultrasonic sensors, they don't see your fingerprint at all, they feel it. Ultrasonic technology uses high-frequency sound waves instead of light or electricity. The sensor fires ultrasonic pulses at your finger and measures how long it takes for those sound waves to bounce back. Because ridges and valleys have different depths, the sound returns at different times. It's sonar for your finger, building a complete depth map in milliseconds. Qualcomm's 3D sonic sensor is the most advanced commercial implementation. It transmits ultrasonic pulses and measures return reflections to build a complete 3-dimensional fingerprint profile, which means it works through screen dirt, grease, and even water. Capacitive sensors need clean contact. Ultrasonic sensors don't care. The security difference is massive. A 2D electrical map can be faked with gelatin or silicone, but a 3D ultrasonic depth map, you'd need to replicate the exact topography of someone's fingerprint down to microscopic ridge depths. Nearly impossible without advanced manufacturing equipment. Most people think all fingerprint sensors work the same way. They don't. Right? Your phone is either measuring electrical changes, photographing your finger, or echolocating its surface geometry. And only one of those methods is mapping depth. At least fingerprint sensors stay in one place. The next sensor is so small and so obscure that most people don't even know it exists, but without it, your phone's flip cover wouldn't work. Hall effect sensor. Your phone knows when you close that magnetic flip case, and no, it's not because of software magic, it's because of a tiny sensor detecting the magnet embedded in the cover, and that sensor is based on a physics discovery from 1879. Edwin Hall figured out something weird about electricity and magnetism. Well, when you run an electric current through a conductor and hit it with a perpendicular magnetic field, the electrons don't just flow straight, they get shoved sideways by what's called the Lorentz force. Those electrons pile up on one side of the material, creating a measurable voltage difference across the conductor. That voltage is called the Hall voltage, and it's directly proportional to the strength of the magnetic field. Smartphones use this exact principle. A Hall effect sensor sits inside your phone, constantly monitoring for nearby magnetic field. When you snap on a protective case with a magnet embedded in the cover, that magnet triggers the sensor. The sensor detects the magnetic field, and your phone instantly knows the case is closed. Screen off. No button press required. No software algorithm trying to guess what's happening. Just electrons getting deflected sideways by a magnetic field and creating a voltage that says, hey, there's a magnet here. And here's the thing. Most people think this is Bluetooth or motion detection or some advanced AI feature. It's none of that. It's a 145-year-old physics principle watching electrons pile up on one side of a semiconductor. The sensor doesn't need calibration, doesn't drain your battery, and works instantly because it's measuring an actual physical force in real time. The Hall voltage tells the phone both the direction and strength of the magnetic field. Strong magnet close by, high voltage, weak magnet or no magnet, low voltage, binary decision, case closed or case open. Simple, elegant, invisible, but if you think detecting magnets is clever, wait until you see how your phone measures distance using lasers that calculate the speed of light in nanoseconds. LiDAR and time of flight, your phone can measure distance by racing light itself. And when I say racing light, I mean literally timing photons bouncing off objects and calculating how far they traveled based on the speed of light, which is insane when you think about it. Here's how it works. Time of flight sensors fire an infrared laser at whatever's in front of your phone, then measure the exact moment the light bounces back. The math is straightforward. Distance equals the speed of light times the time of flight divided by 2. The division by 2 accounts for the round trip. Light travels at 3 times 10 to the 8th meters per second, so we're talking nanosecond precision here. But here's where it gets genuinely impressive. Apple's LiDAR system in the iPhone and iPad doesn't use one laser. It uses 49,152 individual pixels. Each pixel independently measures depth. That's 49,152 separate laser rangefinders working simultaneously, creating a detailed three-dimensional map of your surroundings in real time. Every single pixel is timing light independently. At 3 meters distance, the accuracy is ridiculous. The mean average error is 0.12%. That's precise enough for professional applications. At 10 meters, the iPhone 15 Pro and iPad Pro M4 still achieve approximately 0.5% error, which is still exceptionally accurate for a consumer device, but then physics gets in the way. Beyond 10.9 meters, accuracy degrades dramatically. The iPhone 15 Pro hits 11.6% error, and the iPhone 16 Pro reaches 25%. The sensor is phenomenal at short range and borderline useless past 11 meters, which makes sense when you realize it's optimized for augmented reality, not surveying. The practical result is your phone can map a room instantly. It knows the exact distance to every surface within 10 meters, accurate to within centimeters by measuring how fast invisible light travels. Every AR experience that places virtual objects in physical spaces relies on this nanosecond timing precision. But if you think measuring distance with light is complex, wait until you see how the image signal processor turns incomplete color data into finished photographs. Image signal processor. Your phone's camera is fundamentally broken, and I can prove it. Every camera sensor captures an incomplete image. Each pixel sees only one color through tiny red, green, or blue filters arranged in what's called a Bayer pattern. One color, per pixel, that's it. The raw data coming off the sensor looks nothing like a photograph. It's a mosaic of individual color points with massive gaps where the other two colors should be. Unusable, ugly, incomplete. The image signal processor fixes all of that in milliseconds. The ISP performs simultaneous processing functions that would take a human photo editor hours to replicate manually. Noise reduction suppresses grain in low light images. White balance correction ensures whites appear neutral under any lighting. Auto exposure calculation prevents blown out highlights and crushed shadows. Demosaicising reconstructs full color data by analyzing neighboring pixels and mathematically inserting the missing color information. Contrast and sharpness enhancement makes edges pop. Demosaicising is the critical step. Since the Bayer filter captures only one color per pixel, the ISP has to interpolate the other two colors by examining surrounding pixels. It's educated guesswork at computational speed. A red pixel surrounded by green and blue neighbors gets assigned green and blue values based on statistical patterns. The algorithm does this for every single pixel before you see the image. Modern ISPs integrate machine learning for scene recognition and face detection. Portrait mode blurs backgrounds using depth data and software. Night mode stacks multiple exposures to simulate long exposure photography. HDR combines bracketed shots to preserve detail in highlights and shadows, all processed before you see the photo. Here's where the smartphone camera debate gets heated. Megapixels matter far less than ISP sophistication. A 12 megapixel sensor paired with an advanced ISP will outperform a 48 megapixel sensor with mediocre processing every single time. The sensor captures data, the ISP creates the photograph, and here's the uncomfortable truth. What you see on your screen is not what the sensor saw. It's an algorithmically enhanced interpretation of incomplete data. Some call it computational wizardry. Others call it photographic fraud. The image you share is a product of invisible processing decisions made by software engineers, not a direct capture of reality. Without the ISP, smartphone photography wouldn't exist. The sensor alone produces garbage. The processor transforms that garbage into a finished image in the time it takes to tap the shutter button. If you enjoyed this video and want to see more, click the video on the screen now.